This was a teaser. Thermodynamics and heat transfers are like that only, right? Okay, the maximum amount of the creativity that should come from my side, right? Okay, I did that part, right? But don't get so much worried. In the entire physics, there are lots of chapters, right? Okay, that can be visualized into the funny way, into the most creative way, right? But if I'm talking about the heat transfer in thermodynamics, right? So I think this teaser was a maximum from my side. So don't get worried. Okay, innovation is a part of our industry, creativity is a part of our tech, right? Definitely the new things will come up into the new way next time. Okay, this was just an initiative, right? The teaser. Next time, hope so it is possible that new things may come up with the new way. So thermodynamics, I forgot. Hello bacho, Sat Sri Akal, namaste from my side. How are you all? So this is Indrajeet Singh, your own physics educator, welcoming you all into the most sensible platform, right, for an aspirant, those who are preparing for JEE NEET kind of examination. I must say, right? Are you all ready? So champions, again, myself Indrajeet Singh welcoming you all into the JEE NEET Crash course, and this series was started with the chapter units and measurement, and it was followed by motion in 1D, 2D, and it directly moved on to the slowly we moved on to the NLM, and then we did work energy and power, followed by rotation, and we moved on to the gravitation, slowly to the heat transfer, right, and then the thermodynamics. Okay, after thermodynamics, right, in the crash course, obviously only the two chapters, SHM and waves, are going to remain. Okay, so now thermodynamics, as I said you all in my previous session, right, we are starting from the units and measurement. Obviously it was completely an experimental part. In motion 1D and 2D, we were dealing with the analysis of the motion, but we were not dealing with the cause, right? Okay, when we moved on to the NLM, yes, we were dealing with the cause of the motion, and that was force. Different types of force we saw. After that, with force, even we were dealing with the energies, right? So first, completely an experimental setup. Second, slowly motion without cause, then motion with cause, that is force, and then motion with cause and energy, force and energy. After that, till 6th chapter, we were not considering any configuration of the particle, right? But now in rotation, we consider the entire configuration of the particle and understood the concept of center of mass, moment of inertia, and all of that stuff. After that, slowly we moved on to the gravitation. It was a complete different part, and we reached to the thermal physics. That was a completely different domain. That is, we started with the heat transfer. We saw conduction, convection, radiations, and the relevant laws and everything. Now, as thermodynamics. Now, what is actually, the students always used to get confused between heat transfer and thermodynamics. There is a very less difference between them. In heat transfer, we used to learn about how the heat exchange takes place between the two bodies. What are the modes of the heat transfer? How temperature variations are measured. In thermodynamics, we are going into a deeper part, that if heat exchange is going on between the system and the surrounding, or between the two parties, what kind of the process is it? It is how state variables are involved in it, how pressure in that, see, heat transfer is going on, it's okay. How it is going on, how temperature is getting changed, we saw in the previous chapter, right? But here, how the variations of the pressures are measured, whether the volume of the body is getting changed or not, how the internal energy is associated with it. Lots of things we are going to discuss, right? Lots of things, right? So we are going into the deeper part, but as per our tradition, first of all, let's start with, right, what content we are going to see in this chapter. We are going to deal with, first of all, right, the cases of the equilibrium in the zeroth law of thermodynamics, and then we will deal on right, with the all of the work done for all of the thermodynamic processes. Then with the first law of thermodynamics, relevant work done, second law of thermodynamics, Kelvin, Planck's and the Clausius statements, heat pump and heat refrigerator, and finally we are going to deal with the sums of Carnot cycle. So are you all ready? As per our tradition, right, okay, our session always begins with the teaser and then followed by the flow chart, right? So what will be the flow chart of the thermodynamics? Right, the first part, simple thing, it is the zeroth law of thermodynamics, right? In zeroth law of thermodynamics, equilibrium situations are discussed, right? With the equilibrium situation, its statement is given and its relevant example is given. This is all about the zeroth law of thermodynamics, right? After zeroth law of thermodynamics, obviously, right, we are going to discuss, right, some of the important terms, or directly we can say it's first law of thermodynamics, right? In first law of thermodynamics, right, okay, first thermodynamics, before this thermodynamic processes are discussed, right? With this thermodynamic processes, right, like examples of this thermodynamic process: isobaric, isochoric, isothermal, adiabatic. Work done for all thermodynamic processes, sign conventions of it, right? With the relevant sign conventions, we are having the special graphs. So this is all on the right, the part of the first law of thermodynamics. Now, after first law of thermodynamics, the next part, right, goes to the second law of thermodynamics. In second law of thermodynamics, basically we are having two kind of, right, statements. First was given by the Kelvin and Clausius, right? The next part we are moving on, right, to the heat pump, heat refrigerator and Carnot cycle, right? Okay, right, so this was entire, right, see, it is a very small chapter, right? Okay, it holds the high weightage. Okay, yeah, one thing, the polytropic process and this relevant CP and CV, right? These things we are also going to discuss. So I'm writing it here, right? CP, right? What is CV? How we are going to measure the R? How we are going to define the first law of thermodynamics for all the processes, right? Okay, this thing we are also going to discuss. So this is all. See, the entire chapter is quite small. Some of the limited concepts are there, right? But questions are quite impressive, right? When we'll solve this PYQ, now you'll able to understand that the question from this chapter are quite impressive. They're a bit conceptual also, and right, easy. They're easy, like it is easy to calculate them. It is easily, we can easily right, reach up to the results. Like it's all about you to just identify the phenomena, right? You have to just identify the process and apply the formula. Okay, so this is what the flowchart of the thermodynamics is all about. I'm moving aside. On the countdown of 5, if you want to have a snap of it, it's 5, 4, 3, 2, 1. Now, thermodynamics starts with the zeroth law. And before understanding the zeroth law, let's understand what actual the equilibrium is. Before moving on, right, to the equilibrium, I'm going to give you all in a one simple example to understand this. Right, a very simple example. Okay, I'm having the two objects in my hand. This is the first one, this is the second one. This is the first one and this is the second one. Right now, see, this is at the higher temperature, this is at the lower temperature. When they are brought in contact with each other, suppose this is at the 100 degrees centigrade and this is at the 40 degrees centigrade. So when they are brought in contact with each other, in previous chapter we already studied that if two objects are brought in contact with each other, and obviously if they are having the the temperature difference, right, then through the conduction mode of heat transfer, heat will flow. Similarly, taking one example, this is at the high temperature, this is at the lower temperature, they are brought in contact with each other. As because of the temperature difference between them, right, through the conduction mode of heat transfer, heat will flow. What will be the direction of the heat flow from high temperature to the lower temperature, right? Now, my question is to you all is, for how much amount of time this heat will flow from the higher temperature to the lower temperature? The reason behind this question is, if the object is at the higher temperature, right, heat is flowing from it. So obviously the temperature of the higher object, this higher temperature, right, of the object is going to decrease because it is losing some energy. And on the opposite side, right, if the object with the lower temperature is gaining some energy, right, then temperature of that object is going to increase. So for how much time the heat flow will, this process of the heat flow will persist, will exist, right? So in that case, I want to tell you all, after the t amount of the time, the temperature of the both system will get balanced, right? And one kind of the equilibrium is attained, right? Temperature of the both system, right, will get balanced and one kind of equilibrium is attained. In that equilibrium, right, heat transfer, see, in that equilibrium, both temperature of the both objects will get, right, equal and the heat flow will stop, right? Now, this was a example of a specific type of equilibrium, but it is easy to understand that stuff, what actually the equilibrium is, right? So see, you can see we are having one visualization. One is at the right higher temperature 90, second is at the lower temperature 10. Now when they are brought in contact with each other, the object that is at the higher temperature, the object, right, with the higher temperature, right, that is getting continuously decreased, and the object that is with lower temperature, right, the temperature of it is getting increased. Finally, see, 50-50, one equilibrium state is attained. So that is what actual definition of the equilibrium is. The condition of a system when, right, the condition of a system when neither its state of a motion nor its internal energy state tends to change with respect to time. Now, what actual the internal, lots of students might be having the question in the mind, right? Right, might be having a queries that what actual the internal energy is, right? What actual the internal energy is, because we haven't discussed the definition till now. But don't get worried, in first law of thermodynamics we are going to discuss that stuff. Okay, so the condition of the system when neither state of the motion of whatever particles this material is made up of. Obviously, when the heat is supplied, either there is an absorption of the heat, right, okay, or the heat is released. There is always change into the variation of the variation in the vibrations of the particles is always measured, is always noticed, right? Not measured, noticed, right? So in this case, neither its state of motion nor its internal energy, state of the motion of the particle inside of what this material is made up of, it is not going to change. Neither, in another sense, it is only correlated to the internal energy, right? So state of motion of the particles and internal energy both are not going to change. If this situation is attained, if this attains, we can say system is in equilibrium. Now, what kind of equilibrium? There are some criterias in that. What kind of equilibrium? There are some criterias in that, right? We are going to discuss that part into the detail. But before that, hope so the definition of the equilibrium is, right, okay, clear in front of you all. Now see, types of equilibrium. Basically, three types of equilibriums are there. First, right, it is a mechanical equilibrium, right? Thermal equilibrium, right? The third one, when three of the equilibriums are attained, right, then we are reaching up to the thermodynamic equilibrium. The first one, that is a mechanical equilibrium, right? Second one, it is a thermal equilibrium, right? And as of this visualization, yes. The third, that is a chemical equilibrium. Okay, the third one, it is a chemical equilibrium. Okay, mechanical, thermal and chemical equilibrium. Okay, so how many types of equilibriums are there? Right, basically if we are talking about the equilibrium, then we are having mechanical equilibrium, thermal equilibrium and chemical equilibrium. And with that part, what actual the criteria states regarding the, see, equilibrium definition you all are completely aware of. But if we are moving on to the classification of the equilibrium, right, then we are going to understand some of the important points related to it, right? Some of the important points. Okay, now see. First, thermal equilibrium. Thermal equilibrium, it means that whenever the two objects are in contact or whenever the heat exchange is going on between the two bodies, the final temperature of both of the objects will remain same. If this kind of the situation arises, then we can say the system is in thermal equilibrium. The temperature of the system does not change with respect to time. The most important word, temperature of the system does not change with respect to time. If this situation is attained, then we can say the system is in thermal equilibrium. Mechanical equilibrium, there are no unbalanced forces within the system or surroundings. No unbalanced forces. Mechanical equilibrium, no unbalanced forces are there. Summation of the all forces in x direction is also 0. Summation of the all forces into the y direction is 0. No net acceleration is there. Right? And the pressure in the system is the same at all points. If this kind of situation is attained, we can say system is in mechanical equilibrium. Chemical equilibrium, no chemical reaction takes place in the system. Okay, this is quite easy. We are only interested into the thermal equilibrium because maximum we are going to use that. Three types of equilibrium: thermal equilibrium, mechanical equilibrium, chemical equilibrium. Thermal equilibrium, no heat transfer, no temperature change into the system. Mechanical equilibrium, no unbalanced force exists. All forces will be balanced in x and y direction, and net acceleration in x and y will be completely 0. Chemical, further no reaction will occur. Right? If this of the three, right, if this of the three of the equilibriums are attained, right, then we can say the system is in thermodynamic equilibrium. Right? For system to attain thermodynamic equilibrium, this three should completely satisfy this three, the conditions of the equilibrium. Okay, so this was all about the types of equilibrium. Now let's move on to the most important statement, zeroth law. Mathematically, if I want to represent the zeroth law, then I will say it as, I'm sorry, yes, as because of the, okay, mathematically if I want to represent this stuff, then if right, A is equal to B, B is equal to C, then A is equal to C. Mathematically I have represented zeroth law, but how we are going to define it technically? If A is in thermal equilibrium with B, B is in thermal equilibrium with C. Thermal equilibrium means what? The temperature of the system will not change with respect to time. Mathematically I have represented this. If I want to write in terms of, right, if I want to write into the statement, then if A attains thermal equilibrium with B while B attains thermal equilibrium with C, if this happens, then we can say that, right, A and C are in thermal equilibrium. Right? A and C are in thermal equilibrium. Right? A and C are in thermal equilibrium. Right? Simple. Mathematically, A is equal to B is equal to C, A is equal to C. Simple. In this visualization, you can see A is in thermal equilibrium with C, or in another sense, this in the visualization, C is kept as the intermediate element, right? So for that, if you want to change, and we can, according to the visualization, we can change this thing, right? Right. According to the visualization, we can change this, right? So, right, we'll be able to understand, right, that stuff very well. See, here the C is an intermediate element, right? C is an intermediate element. It is saying that if A is with C, B is with C, then A is with B. If A attains thermal equilibrium with C, while B attains thermal equilibrium with C, then we can say A and B are in thermal equilibrium with respect to each other. A is having A is with C, right? No temperature is changing with respect to time. B is with C, no temperature changes with respect to time. If this exists, if this is attained, then we can say A and B are in the thermal equilibrium with respect to each other. This is nothing else but the zeroth law of thermodynamics, right? Zeroth law of thermodynamics. Now, thermodynamic processes. Okay, we have seen the modes of the heat transfer into the previous session, but how? Using the process, what process the heat exchange takes place, how the state variables are involved in it, right? That actually defines the thermodynamic processes, right? Okay, so how I'm going to define the thermodynamic process? Let us take an example. Suppose, right, this is an object A, right? This is an object B. Obviously, heat transfer is going on from A to B. So my question is how? Right? How? And if heat exchange is taking place, how equilibrium is involved in it, right? Okay. So if I want to define that stuff, then I can say the change in equilibrium of one microstate to another microstate. If this is possible, we can say, right, one process is going on, and that process, right, is thermodynamic process. In another sense, in thermodynamic process, two stages are involved. One, that is initial stage, right, from which, right, okay, heat exchange, there are two stages. First one, it is an initial stage, right? The second one, it is a final stage. Always thermodynamics begins from initial state and reaches to the final state. So change in equilibrium of one microstate with respect to another, right? That defines the thermodynamic processes. That defines the thermodynamic processes. Right? Now, if heat exchange is going on between A and B, or in between system and surrounding, right, then how many processes are there? And if heat exchange is going on, then how work is done? In entire chapter, we are going to deal with only three stuff: work done, right, internal energy, and the heat supply or heat absorbed. Heat released or heat absorbed, right? Those are more specific word in this three, maximum with this three. And for the first law of thermodynamics, we are going to see more than 10 sums, because in entire chapter is all about first law of thermodynamics only, and maximum number of the questions are coming either from first law. Sometimes there is a, we can say, the least probability to commit from heat engine and the Carnot. Even in that, right, the first law of thermodynamics is involved, the parameters of it are involved. Right. So isothermal process, what actual the isothermal process is, right? Isothermal process states that temperature of the system is kept constant, right, when the temperature of the system, right, is kept constant, right, then we can say that pressure is inversely proportional to volume, right? Pressure is inversely proportional to volume. In another sense, PV is equal to constant, right? Why it is constant? Because nRT value is constant. First, if pressure will increase, volume will decrease, and this will go on vice versa. So when the temperature of the system is kept constant, when the temperature of the system is, suppose the temperature of the system is kept constant and heat exchange is going on, is it possible? Is it possible? Right? Is it possible without heat exchange, without temperature difference, right? The heat flows. Is it possible? So here I want to tell you about not only the heat exchange, right? The three of the most important parameters plays the important role. The first one, that is first law, or this one, heat supply. Second one, that is the internal energy and work done. Here I'm not saying that as because of the temperature difference the heat is flowing between the two objects, right? But we are talking about the heat supply from some else source. That is the difference, right? Students always used to get confused in between these 2 points. There is always, right, heat supply. Either heat is getting supplied from external source to the system, right, or this thing is getting released. So in that case, what is the surrounding temperature, right? So if the temperature of the system is kept constant, right, so the variation into the pressure and volume are measured like this way. So can I say initial stage P1 V1 is equal to constant, right? Because if we are talking about the, see, isothermal process is a thermodynamic process, na? So obviously the equilibrium state is going to change from one to another, right? So at initial state, the process always initiates from initial stage and, right, discards to final stage. So in initial stage, PV is equal to constant. At final state, P2 V2, that is equal to constant. So for the thermodynamic process, can I say PV, that is equal to constant, that is equal to P1 V1, and that is equal to P2 V2. PV is equal to constant, that is equal to P1 V1, and that is equivalent to P2 V2. Right? Isothermal processes. Now, if I'm talking about, let us take an example. Okay, let's keep this aside. That is because of the temperature difference, the heat is getting flow. Now I'm talking about the system that contains the ideal gas. Let us take an example to understand this. System that contains the ideal gas. Right? Ideal gas is present inside it. If we are talking about the temperature difference, then between system and the surrounding, there exists a temperature difference. But if I'm talking about the temperature of the system, if it is kept constant, right, then pressure and volume varies with this equation. Pressure and the volume varies with this equation. Suppose, let us take an example, one piston is kept, right, at the top of the ideal gas, right? One piston is kept. This is a piston, right? If you have seen the ad of ECG, engine, clutch and gear, right, continuously the thing that is in the rotatory motion, right, that is a piston. It compresses the fluid. It compresses the fluid, right? Generally piston compresses the fluid. If I'm talking about our day-to-day life, then this kind of the piston is present into our motor gadis, right? Generally they used to compress this fluid and generate a spark, right? Okay, generate an energy through which, right, our vehicles are in motion, right? Vehicles attains motion. So suppose this ideal gas is present inside it and one piston is there, we are trying to compress it. Suppose this entire thing is going at a constant temperature. We are not doing that much amount of the compression, but right, if entire thing is going at the constant pressure or constant temperature, right? So can we say that? Yes, we can say that, right? The PV of the system, the pressure is inversely proportional to volume. Pressure is increased, volume will decrease, volume will increase, and pressure will decrease. So what will be the right graph, the PV graph for that, right? What will be the VT graph for that, right? And what will be the PT graph for that? PV graph would be like this way. Pressure is high, volume is low, volume is high, pressure is low, right? VT graph is like this way. Either volume increases, right, or decreases, right? Temperature of the system is kept constant. So either, right, volume increases, right, or decreases. Either volume increases or decreases, right? And if I'm talking about the pressure, right, again the temperature is kept constant, so like this way, pressure is increased, right, or pressure is decreased. So that's why this graph doesn't make any sense. If you want to plot T versus P graph, we are having like this way. If you want to plot T versus V graph, then we are having like this way, right? Okay. Okay. Only, right, this graph makes sense for the thermodynamic process, right? Else are just for the information purpose, not more than that. Now, how much amount, if temperature of the system in this case kept constant, and how much amount of the work is done? We need to calculate that, right now. We need to calculate that stuff by using the formula. So work done. See now. Here, pressure is inversely proportional to volume. So here, the work, whatever amount of the work is there, that work is not as because of the constant force. So I can't write down this equation W is equal to F dot D. No. I can only write this equation if work is done by the constant force. Here, the force is not constant, right? So I am defining it as dW is equal to PdV. Why the force is not constant? I can't say within 2 minutes if the pressure is changing to some X value, then in next 2 minutes, right, the pressure will change to same value of X. No. The things that are changing are not uniform. Neither the change in pressure is uniform, neither the change in volume is uniform. So dW, that is equivalent to PdV. So here work done, can we say that integration of PdV, right, from V1 to V2, initial to final. So here work done, right? Okay, here work done. So I am replacing it from V1 to V2, right? PdV, right? Now, according to the isothermal process, can I say PV that is equal to constant, right? So PV that is equal to, let us take an example, it is C. So how can I replace this P, right? We can replace this P as C by V, right? So replacing this equation into the equation of work done, we are getting C by V into dV. So here, what will be the value of work done? The work done, that will be integration of V1 to V2, right? C by V into dV. Now this will be, right, suppose if we are integrating, right, then we are getting it as C ln of V, right, limiting from V2 to V1, right? So here work done, it would be C, right, and it will be ln, right? Okay, if I'm talking about this V, then we can say, right, according to the property of log, I can replace this thing by ln by V2 by V1. Now, okay, I'm replacing C according to the process, right? nRT in this process is kept completely constant, right? So can I replace here C as nRT, that is ln of V2 by V1. This is the work done, right, into the case of the isothermal process, right? Work done in case of isothermal process, right? Now suppose if you want to get the final equation, right, then it is 2.303 nRT. If we are replacing the natural log to the log to the base 10, we are having V2 by V1, right? So this is the equation of the work done for the isothermal processes. Right? Okay. So this is the first thermodynamic process. Now let's move on to the next thermodynamic process, that is adiabatic process. And how we are going to identify, how we are going to define that work done. Right? The adiabatic process states that, what does it state? The net heat flow of the system is 0, or, right, process occurs very rapidly. Generally, whenever you used to see this lecture now, whenever anyone who is explaining the thermodynamic process, they always used to say the net heat flow is 0. From the system, the net heat flow is 0. Or in another sense, you can say, suppose this chamber is insulated. If I am saying this chamber is insulated, it means from the system no heat flow is going to happen. If chamber is insulated, from this system no heat flow is going to happen, right? So in that case, why no heat flow? The reason behind this, right, will define the adiabatic process. The reason behind it will actually define the adiabatic process. Why there is no heat flow? Because the process occurs very rapidly. If I'm talking about, say, this is the same example of the piston. If piston is moving up and down at the very high rate, I'm talking about that moment at the very high rate such that system does not get time to exchange the heat. Most important point. System does not get time for heat exchange, right, as it is a very quick process, right, as because of this quickness, right, okay, the system is not able to, a system will not get as much amount of the time to exchange the heat. That's why the net heat flow is 0. Equation of the adiabatic process is PV raised to gamma, that is equal to constant. This is the equation of the adiabatic process, right? This is the equation of the adiabatic process, right? Now, the PV graph, right, of the adiabatic process is also like this way, but there is a difference, right? There is difference between the graph of the isothermal and the graph of the adiabatic process. There is a difference. Area of someone is bigger, area of someone is less, but that thing, that comparison we are going to see into the sums, right? Now, what is an actual work done? Basically, there are three equations of the adiabatic process, right? First of all, suppose if we are talking about, right, in the system, right, one ideal gas is present, and that is represented by PV is equal to nRT. The ideal gas is represented by PV, that is equivalent to nRT, right? PV, that is equivalent to nRT. I'm sorry for that. Okay, now in this case, suppose, right, there is a no heat flow in the from the system, and it is like cover up in an insulated chamber. It means that, right, process is going on quite quickly, right? Rapid process is going on in that case, right? It is an adiabatic process, right? The equation is represented at PV raised to gamma is equal to constant. Sometimes apart from this, right, okay, there are two another formulas on which sums are asked, the numericals are asked. Suppose if I am making the subject, right, P, that is equal to nRT by V, and replacing in equation number 1. Can I consider this is equation number 2? Yes. Replacing equation 2 in equation number 1. What we will get, right? It's nRT by V, and V raised to gamma is equal to constant, right? In another sense, right? Okay, this will be T V raised to gamma minus 1, that is equal to constant. This is the second equation of the adiabatic process. If you want to measure the variations, right, of pressure and volume, you can take this equation. If you want to measure, right, the variations in volume and temperature, you can take this equation. Now suppose, right, from equation of an ideal gas, can I replace V is equal to nRT by P? Right. Can I consider this is equation number 3? Right. Replacing 3 in 1. What will get P into nRT by P is equal to whole to the power gamma is equal to constant. Right. And here it is P1 minus gamma T whole to the power gamma is equal to constant. If you want to analyze the adiabatic process and want to measure the variations, right, and if you want to show the relation between the pressure and temperature, then this is the equation. Now students might be having the question, what actually the gamma is? Gamma is adiabatic index. Generally it is defined as Cp by Cv. The specific heat at the constant pressure, specific heat at the constant volume ratio of that. Generally for adiabatic process, it is always taken as 1/4, right? Exceptions are always welcome, and they will be mentioned into this question. Generally the adiabatic index is 1.4, but if it differs, it will be mentioned in this question, right? So these are the equations of the adiabatic processes. Now let's move on to the actually work done. Same. If the net heat flow is 0, whatever kind of the work is done, it is not done by the constant force. So it means we are using this equation PV dW is equal to PdV, and this work done, that is integration of PdV. From this adiabatic process, can I replace this stuff as, okay, we are replacing this limits, the C by V to the power gamma into dV, right? C, this will be V to the power minus gamma plus 1 whole divided by minus gamma plus 1, right, limiting from V1 to V2. Okay, so W is equal to C, right? Can I replace it as V2 whole to the power minus gamma plus 1 minus V1 whole to the power minus gamma plus 1 whole divided by, right, minus gamma plus 1, right? Now can I consider this as equation number 1 now? According to the equation of the adiabatic process, P to the power gamma is equal to constant, right? And that is equal to P1 V1 raised to gamma, and that is equal to P2 V2 raised to gamma, and is equal to constant C. Suppose if C is multiplied inside, so we are getting the final equation as CV2 whole to the power minus gamma plus 1 minus CV1 whole to the power minus gamma plus 1 whole divided by minus gamma plus 1, right? So can I consider this as equation number 2 from 2? Can I replace W is equal to P1 P2 V2 whole to the power minus gamma plus 1 V2, P1 V1 whole to the power minus gamma plus 1, right, whole divided by minus gamma plus 1, right? So finally we are getting the equation of the work done as P1 V1 minus P2 V2 whole divided by, right, gamma minus 1, where gamma is an adiabatic index. This is work done in adiabatic process. Work done in adiabatic process, right? So this is what all about, right? Now let's move on to the third type of the thermodynamic process, right? That is isochoric process. Now in isochoric process, obviously there is one thing, volume of the system is kept constant. If ideal gas is placed into the cylinder and one thermodynamic process is going on in which the volume of the cylinder is kept constant, right? Volume of the cylinder is kept constant, right? So I must say, if volume of the cylinder is kept constant, then work done, that is equal to P delta V, right? And that is N delta T, right? If the volume is getting constant, work done in isochoric process is 0. Work done in isochoric process is 0. It means what will be the graph? Suppose if you want to T versus V graph, right? Okay, I'm sorry, V versus T, otherwise we will have the infinite slope, right? It's V versus T graph, right? It will be like this way. If you want P versus V graph, right? See, work done is 0, right? Slope is 90 degree, it is infinite, right? Slope that is equal to infinite, 90 degree, 10 of 90, right? Okay, so this is of the isochoric process, volume of the system is kept constant. Now the last process that is that is happening at the constant pressure, that is isobaric process. Process that happens at the constant pressure, right? Work done for that is equal to nR delta T, right? Constant pressure, or in another sense we can say P delta V, right? This is the work done, right, for the isobaric process. Now what will be the graph? I think you all are aware of, we are not wasting time in that, right? Now let's move on to the most important thing, that is a polytropic process, right? This is a general definition for all processes. If the system is getting compressed, or whatever the heat is supplied to any system, right? Okay, whatever the heat is supplied to the system. Now what happens here? This polytropic process is defined as PV raised to N, that is equal to constant, where N is defined as polytropic index, right? N is defined as polytropic index. Value of the N, this is a kind of the general case. Value of the N is getting changed, we are getting the different processes. How? See, first, suppose, right, if N that is equivalent to 1, then we can say PV is equal to constant. Then this process is isothermal process. Then this process, it is known as what? Isothermal process. Second case, right? If N is equivalent to 0, pressure remains constant, then this process, it is isobaric process. Isobaric process. The third case, right? Okay, the third one, suppose if N value that changes to 0, then this part will be, if N value changes to infinity, then this part will be 0. It means, right, okay, and this will be isochoric process, right? This will be isochoric process. Now the fourth right process of this, right, we can say it as, if N value, right, that is changing to gamma as the adiabatic index, then PV to the power gamma is constant, right? Then we are defining it as an adiabatic process, right? So using the polytropic process, right, we are going to, right, understand the four most important thermodynamic process in which the value of the, right, polytropic index is getting continuously changed, or not continuously changed, but it is getting changed. If the value of the polytropic index gets changed, right, okay, the process gets changed. This is what our about the polytropic process. Now what is work done for the polytropic process, right? Procedure is same, dW is equal to PdV, right? Limiting from 1 to 2, right? Now if I'm replacing the equation of the polytropic process, limiting from V1 to V2, then it is C by, right, V to the power N, and that is dV. So this work done, this will be C ln of, not ln, I'm sorry, right? It is C, right? And that is V to the power minus N plus 1 whole divided by minus N plus 1, right? Limiting from V2 to V1. Similarly, work done, that is equal to C V2 minus N plus 1 minus V1 minus N plus 1 whole divided by minus N plus 1, right? Minus N plus 1. So here, according to the this phenomena, this polytropic process, P1 V1 to the power N, P2 V2 to the power N, its PV to the power N is equal to constant, right? So in that case, work done, we can write it as P1 V1 dot V1 to the power minus N plus 1 minus, I'm sorry, we need to write V2 first to evaluate it easily, right? It's V2 V2 V2, and this is P1 V1 to the power minus N plus 1 dot V1, right, whole divided by minus N plus 1. So finally we are getting the work done as, right, P1 V1 minus P2 V2, right, whole divided by N minus 1. This is the work done for the polytropic process, right? This is the work done for the polytropic process, right? Now after that, let's move on, right, to the most important part, that is first law of thermodynamics. And before moving on to the first law of thermodynamics and its relevant sums, right, first of all, let's identify what actually the internal energy is. The energy that is associated with internal configuration of the system, energy that is associated with internal configuration of the system, right? Then this kind of the energy, it is defined as the internal energy. You can see this thing into the right visualization. We can see this thing into the visualization. It's very simple stuff, right? We can see this thing into the visualization. A very simple thing, right? Okay. Now, before moving on to the first law, we need to take one example, right? And let's have a glimpse what we have studied till now, right? Rapidly, we are going to see, right, what we have studied till now, so that, right, we are able to understand that first law of thermodynamics, as it is quite important. See, this is an entire flow chart, okay? And thermodynamics, it starts from zeroth law, first law, all of the work done, second law of thermodynamics, and heat pump and refrigerator and Carnot cycle, right? 2, 3. After that, we moved on to the zeroth law. Before moving on to that, we understood what actually the equilibrium is, how many types of equilibriums are there, right? And after that, the zeroth law, and then we moved on to the thermodynamic processes, right? We saw the actual definition of the thermodynamic process, and after that, right, we moved on, right, to the types of the thermodynamic processes and the relevant work done, right, and their related work done. I'm sorry, right? The first one is isothermal process, second was what, this work done, okay? The next was, I think this is getting okay. Some issues are there as because of the visualization. I'm extremely sorry. After that, we moved on, right, to the next type of the process, that it is an adiabatic process. We moved on to the work done. Then we moved on to the isochoric process. It's relevant work done. Baric process is relevant work done. Polytropic process, it's relevant work done, and how the value of the polytropic, right, index is getting changed. Internal energy. Now let's move on to the, right, first law. Before moving on to the first law of thermodynamics, I want to take a very simple example. Furnace. Right? Furnace. There is one furnace like this way. Right? Okay, we are having the gate like this way. Okay, we are having the gate like this way. Okay, we are, I'm talking about, yes, I'm talking about the furnace. Right? Platform is there, right? I'm talking about the furnace. Okay, see, in furnace, what happens here? Right, in furnace, the furnace temperature is at approximately, right, 1000 degrees centigrade. The furnace temperature is approximately 1000 degrees centigrade. Now what happens here? Suppose if we are taking one metallic rod, right? If we are taking one metallic rod, right, inside that furnace, right, metallic rod inside that furnace. If we are taking one metallic rod inside that furnace, right, now what will happen here? Heat from the furnace, first point, heat is supplied to the rod. As because of that heat supply, temperature of rod is going to increase. Rod is kept inside the furnace. Furnace temperature is 1000. Rod temperature is less. Right now, the temperature of the rod is going to get increased. Right? Some part of the rod will get melt. It means what will be the final stage? Right? Rod will appear like this way. Half of the thing, it will get melted and it will be, the color will be changed, right? This much amount of the, see, entire rod is not melted, but some part of the rod will get melt, right? And the color changes, right? Some part of the rod gets melt and the color changes, right? Some part of the rod gets melts and the color changes. So it means heat is supplied to the system, some amount of the work is done, and with this some amount, right, whether, right, see, on melting of the rod, obviously, right, there is change in the internal configuration of an object. It means internal energy is getting changed. So from this examples, we can say three important parameters are involved in this process. First, that is heat supply or it is heat released. Second, work is done on the system or by the system. And third, the internal energy. These three important parameters plays a prominent role in any thermodynamic process. Right? Now, how these things are correlated? We are going to see that stuff into the first law of thermodynamics. What it states that Q is equal to U plus delta U plus W. Q is equal to delta U plus W. This is the first law of thermodynamics. How we can justify this statement as a first law? Whenever the heat is supplied of the system of that value, some amount is work done, some amount will change the internal configuration of system. And let's move on, let's move back to the same example of a rod and the furnace, when the rod is kept inside the furnace at the furnace temperature, right? Okay, now what will happen? Some part of the rod will get melt. It means work was done by an external agent or work was done by an heat, and that was the part of Q. And there is a small change into the configuration of the system. There is a change. The part of the rod that is getting melted will change the configuration of the system. It means internal energy of that part is getting changed. right? So that show whatever amount of the heat you are supplying, among that some part of that heat supply work is done and some part will change the internal energy of the system. In theoretical no loss is considered. Theoretical aspects, right? Practically always loss is there. There is no 100%. See, efficiency of any process is never 100%. No, that's not possible, right? That's not possible, right? So a theoretical aspect we can say, right? So this is what the statement of the first law of thermodynamics and no loss is considered. Now, how we can define the first law of thermodynamics for all of those processes? See, if I want to write down this equation, right, then we can write this Q as NCP delta T, delta U as NCV delta T, and work done, right, it completely depends whether it is nRT, right, whether it is the area under the graph, lots of things are there, right? So through this we are going to define this first law of thermodynamics for all processes. First, isothermal process, right? Isothermal process. For isothermal process, can we say that PV that is equal to constant, right, and temperature of the system is completely constant. So in that case, if temperature of the system is constant and NCV delta T, right, NCV delta T, this is 0, there will be no change in internal energy of the system. Delta U will be completely 0. So according to the first law, Q is equal to delta U plus W. Whatever amount of the heat is supplied is completely a work done. For adiabatic process, heat flow is 0. It means whatever amount of the delta U is there. See, Q is equal to delta U plus W for adiabatic process. If net heat flow is 0. Why net heat flow is 0? Because the process is quite rapid. So here, can we say that Q is equal to delta U plus W, right? In this case, if Q is 0, so whatever amount of the work is done, that will be stored into the negative of the internal energy. This is how we are defining the first law of thermodynamics for the adiabatic process. Third process, right? Isochoric process. For isochoric process, can I say, right, work done of the system is 0. Why? Volume of the system is kept constant. So it means work done is 0. So whatever amount of the heat is supplied, right, it is equivalent to delta U. Whatever amount of the heat is supplied, that is equivalent to delta U. The fourth process, that is isobaric process, right? In isobaric process, pressure is kept constant, right? And if pressure is kept constant, then obviously Q is equal to delta U plus W. We are going to measure the variations in all, right? Okay, so that's a general equation, right? It completely depends on case to case and values, how they are getting changed, right? So this is the first law of thermodynamics for all kind of the processes, right? Now, basically, see, now we are going to solve the questions of the first law of thermodynamics, and before that, two most important things are remaining. First one, there are some special PV graph. For that, right, we are having the direct shortcuts, and those kind of graphs are already asked into the examinations, right? We are going to see that as the PYQs also, right? But there are some graphs. Let us take an example. Okay, first of all, before moving on to the graph, right, let's move on to the sign conventions of it, right? So it's all about the sign conventions first, right? Let's move on to the sign conventions, okay, because they are the most important part, right? See, for any kind of the thermodynamic process, these are the general sign conventions, right? If I'm talking about the heat supply, when the delta Q is taken as the positive, when the heat is supplied to the system, when it is taken as negative, when heat is drawn from the system. When delta W is positive, when work done is by the system expansion, it means it is positive. When work is done on the system compression, it is negative. Delta U is positive when temperature increases, and when temperature decreases, delta U is negative. These are the basic sign conventions. And if we are talking about the graph, right, okay, if it is clockwise, if the process is going on clockwise, then work done is positive, and if the process is going on in anti-clockwise, right, okay, if the process is going on in anti-clockwise, right, then work done is negative, right, anti-clockwise the work done is negative. So these are the common sign conventions, very simple. Q, supplied positive, released negative. Work done by the system on the system, by the system positive, on the system negative. Right. Third one, temperature increases, delta U positive, temperature decreases, delta U negative. Right. For graph we are having like this way. See, now we are having the spatial graph. Suppose if I am talking about one PV graph, just keep one thing into the mind. Area under the PV graph is always work done. Area under PV graph is always work done. Suppose this kind of graph is there. This is an initial volume of the system V1. This is an final volume of the system V2. This is the initial pressure of the system P1. This is the final pressure of the system P2. If this kind of the system is there, then here we are having the direct formula of the work done, that is equal to pi by 4, right? V1 minus V2 whole divided by RA into P1 minus P2. This is a direct formula of the work done, right? Now further it depends on expansion or the compression. It's okay, right? So this is a direct formula of the work done. So this is the first spatial case. Suppose if we want to move on for the second spatial case, right? If PV graph is mentioned like this way, right? If it is in rectangle, okay, then this is V1, this is V2, this is P1, this is P2, right? So in this, work done directly can be given as, right, V1 minus V2, right, into P1 minus P2. We are having a direct formula for this, right? Area under the PV graph. Now if I am talking about the third kind of the graph, right, because this kind of the questions, right, are going to come. Suppose the graph is like this way, right? This is a PV graph, right, and this is V2, and this is V1, this is P1, and this is P2. So in this case, work done can be given as half, right, P1 minus P2 into V1 minus V2, right? This is the formula of the work done. So for this, see, three spatial graphs are there, and for this three spatial graphs, right, okay, we are having the three different values of the work done. Suppose if graph is non-uniform, we are not having any kind of symmetrical structure in front, then for all kind of the graph, right, okay, for the remaining graph, the area can be calculated by using the integration. dW is equal to P dV, right? By using this, right, we can calculate this area. Okay, so these are the see, so this is the first law of thermodynamics. First of all, we moved on to the definition of internal energy, then we moved on to the first law, then first law for all processes, PV graph, some of the spatial PV graphs, sign conventions. Now let's move on to the sum of the sums related to the first law of thermodynamics, and after that we will move on to the second law and the Carnot cycle and the respective efficiencies, right? A system is taken, see, system is taken from A to C. A is initial state, C is final state. A is initial state, C is final state. Two paths. This is path 1, this is path 2. The internal energy at A is this, okay, along the path ADC, along the path 1, right? If I'm talking about the path 1, then we are having dq of 1, that is equivalent to 50 joule, right? The amount of the work done dw1, that is equivalent to 20 joule, right? Whereas along the path ABC, if we are talking about the path 2, right? If we are talking about the path 2, right? Okay, then dq2 value is 36 joule, right? Then amount of the work done into the path 2 is equal to how much? Very simple case. See, answer. See, this question is asked in Karnataka NEET 2013. How we are going to solve this? I want to write down one statement note. Change in internal energy never depends on path taken. Change in internal energy never depends on the path taken, right? It depends on initial and final temperatures. It only depends on initial and final temperatures. Suppose in between initial and, if I'm talking about initial and final states, let's take an example. This is an initial stage, this is a final state. Suppose this is my first path, right? This is the second path, this is the third path. In all of those three processes, if the temperature at the initial and final state is not getting changed, right, then it doesn't matter from which path the gas is doing the work done. Delta U will be same for all. Suppose this is a process 1, this is process 2, this is process 3, then delta U will be same for all. Same in this case. Initial stage is A, final stage is C. So temperature at A and C are going to be same. So from whatever path you will move on, the gas will undergo this process from whatever path, right? Delta U is going to be same for all. So applying the first law of thermodynamics, applying according to the first law, can I say for path ADC, right, dq1 that is equal to du plus dw1. What is the value of dq1? 50 and 20. So can I say this is 50 joule and this is du plus 20 joule. So value of the change in internal energy, that is equivalent to 30 joule. Now du will be same for the process ADC, for the process ABC, for both of these processes, right? For both of these processes, this is going to be same. So in that case, what will happen, right? So in this case, right, what will happen? A very simple thing, right? Du, that is again applying the first law. So it's dq2, that is du plus dw2. This is 36 joule. Change in internal energy is 30 joule plus dw2. So final we are getting dw2, that is equivalent to 6 joule. And this is the perfect answer for this specific question. Applied first law of thermodynamics is applied. This question is asking Karnataka NEET 2013. We are going to see more than 10 sums and lots of variations are going to come, right? Lots of variations are going to come and you're really going to enjoy. In all of those sums, right, based on the first law and this concept, right, lots of variations are going to come. The internal energy change in a system that has absorbed 2 kilocalorie of the heat and 500 joule of work. Heat absorbed 2 kilocalorie, 2 into 10 to the power 3 calorie. Now both are not in same unit system. One it is in joule, second it is in calorie. Can I convert? See, 1 calorie that is equal to 4.2 joule. So here Q that is equal to 2 into 4.2 into 10 to the power 3 joule. So it is 8400 joule. Total amount of the heat absorbed by the system is 8400 joule. Now 500 joule of work is done. We need to calculate the change in internal energy. Simple, directly according to the first law of thermodynamics. Right? Q is equal to delta U plus W. What is a Q? 8400. Delta U we need to calculate. What is W? Given into the question 500 joules. right? So delta U, that is equal to 7900 joule. C is the perfect answer. This much amount of the internal energy change will occur, right? This much amount of the internal energy change will occur. Simple. 110 joule of heat is added to the gaseous system. How much amount of the heat is added? 110 joule. Very simple. Change in internal energy is 40 joule. Delta U, that is equal to 40 joule, right? Then the amount of the external work done is, according to, we need to calculate the work done according to first law of thermodynamics, right? According to first law of thermodynamics, right? We are having Q is equal to delta U plus W, right? We need to calculate the work done, that is Q minus delta U, that is 110 minus 40. We are having work done that is equivalent to 70 joule. This is an external work done by the system. B is the perfect answer for this specific question. Simple. We are applying the first law of thermodynamics. First law is of the thermodynamics is the consequences of conservation of energy. Basically, we are having only 4 laws, right? The law of conservation of energy, law of conservation of charge, law of conservation of linear momentum, and law of conservation of angular momentum. Indirectly, right? Okay, we are not moving on to that statement, but just keep one thing into the mind. The first law of thermodynamics is nothing else but a conservation of energy. You can see this statement, na? We are dealing with different forms of energy. And why it is a consequence, right? Energy of system plus surrounding is conserved. Energy of both system plus surrounding is conserved. So that's why it is the consequences of conserve. The first law of thermodynamics is consequences of the conservation of energy. 2 cylinders. This question is quite important. See, this kind of the theoretical question is asked in NEET 2020, latest one. 2 cylinders A and B are of the equal capacity. Cylinder A, cylinder B, both are of the equal capacity. 2 cylinders A and B are connected to each other by a stopcock. They are connected to each other by stopcock. There is a stopcock. Right? Entire system is thermally insulated. A contains an ideal gas at standard temperature and pressure. B is completely evacuated. A contains the ideal gas, right? B is completely evacuated. Both the entire system is thermally insulated. The stopcock is suddenly opened, then what will happen? Guys, 2 cylinders, 1, 2 connected by this stopcock. One contains the ideal gas, second is completely evacuated. We are opening the stopcock. Just keep thinking this thing into the mind that all the walls are thermally insulated. Thermally insulated, it means what? No net heat flow is there. It means what? This will be the quite rapid process, right? Quite a rapid process, and it is an adiabatic. Thermally insulated, no heat exchange from the system. And if you are opening this stopcock, right, the process will go on, right, quite in a very less amount of the time. So this phenomena, it is the adiabatic process. In which of the following process heat is neither observed? See, the same question, but into the different way. In one NEET 2020 situation was given, right, and NEET 2019 it is directly asked. in which of the following processes heat is neither absorbed in the system neither released? I don't think so. I need to tell upon all of those answers. It is nothing else but an adiabatic process. Right? Okay. Here comes the very good question into the NEET 2018. It's really nice. Right? We are going to see some graph based question also. Lots of things we are going to discuss. Right? Okay. See. The volume of a monoatomic gas varies with the temperature. Graph of a volume of a monoatomic gas. See, it is given. Monoatomic gas. Right. Now here comes the concept of degrees of freedom. Degrees of freedom you all are aware of. Degrees of freedom means in how many ways, right, a molecule can perform the orientation and can get displaced. This word displacement is important. Monoatomic gas, right? Okay, they are having the degrees of freedom 3. One rotational, one vibrational, like that way there are the 3, right? Okay. Transitional, yes, 3. Okay, 3 degrees of freedoms are there. 3 degrees of freedom. For diatomic gas, 5, at the higher temperature, 7. Right? In that much way, they can perform the orientations, right? And they can get displaced. So here, suppose if it is a monoatomic gas, see, there is a data. We have seen that, na, polytropic index, gamma, that is equal to Cp by Cv. Now this thing you all are aware of, right? But I'm showing you all in a quick way. Suppose if I'm talking about the monoatomic gas, right? For monoatomic gas, right, we are having Cp. I'm sorry, Cv, that is equal to 3 by 2 of R, and Cp, that is equal to 5 by 2 of R. For diatomic gas, right, Cv, that is equal to 5 by 2 R, right, and Cp, that is equal to 7 by 2 R. Generally these two are there. Apart from this, for triatomic gas, for we are having a linear and non-linear molecule. For one we are having 3R, 4R, right, and for one linear molecule, right, okay, another value is there. Okay, so gamma is equal to Cp by Cv, this thing is there. Okay, apart from this, Cp minus Cv by R and lots of things are there. Okay, volume versus time temperature graph is given. The ratio of work done by gas to heat absorbed. When it undergoes state change from A to B. Work done by heat according to the first law of thermodynamics. According to the first law of thermodynamics, work done by heat, can I write it as Q minus delta U by heat supply? Right? Can we say this is NCP delta T minus NCV delta T whole divided by Q NCP delta T? Right? If I'm making these things right, W by H, that is equivalent to N. Delta T will be common, that is Cp minus Cv whole divided by NCP delta T. N delta T and delta T is going to get cancelled. Cp minus Cp, right, whole divided by. What is the value of Cp minus Cv? That is R by Cp, right? What is the value of the Cp for the monoatomic gas, right? So for the monoatomic gas value, for monoatomic gas, Cp, that is equal to 5 by 2R, right? It's 5 by 2R. So that will be equivalent to R whole divided by 5 by 2R. This R will get cancelled. Work done by heat, that is equal to 2 by 5. And that is the perfect answer for this specific question. Using the first law of thermodynamics and the graph based question, right? 2 by 5. A is the perfect answer for this specific question. Next part. 1 mole of an ideal monoatomic gas undergoes the process described by, see, one polytropic process is coming. NEET phase 2 2016. PV whole to the power cube, that is equal to constant. Right? PV whole to the power cube, that is equivalent to constant. The heat capacity of the gas during this process. We are having the direct formula of the heat capacity of gas. Right? If you want to calculate the heat capacity of gas, that is Cp whole divided by 1 minus x. This is a direct formula. Hey, see, in many of the resources, the derivation of this is given, but we are not interested in that right now. Okay. So this heat capacity C is equal to Cv plus R by 1 minus x, where x is a polytropic index. X or the n. Right, x or n, whatever you want to take, it's okay. Right, so it's Cv. Cv for the monoatomic gases is 3 by 2 R plus R whole divided by 1 minus what is an x value? 3. Right, okay, so we are having the heat capacity as 3R by 2, right, minus R by 2. So value of the heat capacity, that is equal to R. D is the perfect answer. You can see how much easy is the first law of thermodynamics and how these questions, right, how much easy questions are coming. Direct formula, some of might be logical, but rest are direct formula based. An ideal gas is compressed to initial, okay, an ideal gas is compressed to half of its initial volume. Initial volume V, final volume V by 2. Gas is compressed, this much data is given into the question, by means of several processes. Which of the process results the maximum work done? 5 type of processes are there, right? 4 type. Polytropic is the general one. 4 types: isothermal, baric, choric, and adiabatic. See, I'm going to show you one graph, PV graph. According to the first law of thermodynamics, if I'm talking about an isothermal process, this is an isothermal process, and this graph that we have plotted, the curve that we have plotted, it is known as isotherm. It is known as what? Isotherm. Right? It is known as what? Isotherm. Right? Now, this is A to B. In isothermal process, right, temperature of the system is kept constant. Right? Delta U is equal to 0. Whatever the heat is supplied, the same amount of the work is done. But if I'm talking about the work done for the adiabatic process, right, it is more as compared to the isothermal process, right? Okay, area under the curve of adiabatic process is more as compared to area under the curve of adiabatic process is more as compared to isothermal process. As compared to isothermal process. Right? So in this case, what will happen? Right? In this case, what will happen? It's a very simple thing. Right? Area, the work done by the adiabatic, obviously it is going to be greater than work done by isothermal. If I'm talking about one graph. Now, for the isobaric, this is an isobaric process. Work done is a straight line. For isochoric, right, we are having the graph as just this straight line where work done is 0, right? The graph of the isochoric process is like this way, right? So this is actual a graph. If it reminds us about the polytropic process, what was the equation of the polytropic process? P is equal to N is constant, right? If we are taking the N of value as gamma, we are having the adiabatic process. If we are having N value as 1, we are having isothermal process. You can see the value of the N index of an adiabatic process is more as compared to the isothermal process. Here isobaric process N that is equal to 0, and for isochoric process N that is equal to infinity, right? Okay, so it means that we can say work done on the gas which is by adiabatic process, work done is maximum. Just keep this thing in your mind whenever we are calculating for one single gas. If it undergoes from 4 different processes, one gas, same conditions, right? But it has to undergo from the 4 different processes. It means that it is very simple, work done is greater in the adiabatic process. Below figure shows the 2 paths that may be taken, right, from A to C. See, gas is taken from A to C. A is an initial stage, right, and C is the final stage. Okay, in process AB, right, 400 joule is added. If I'm talking about process AB, Q of AB that is equal to 400 joule. If I'm talking about the process BC, Q of BC that is equal to 100 joule, right? Now, what is the heat absorbed by the system in process AC? Okay, so first of all, for process AB, according to the first law of thermodynamics, Q is equal to delta U plus W. But process AB is an isochoric process. You can see AB, constant volume process, it is an isochoric process. So work done is 0. So whatever amount of the Q will be there, it will be delta U. So the change in internal energy in this process, that will be equivalent to 400 joule. U1, I am considering it as a U1. Now for process BC. Now BC is a constant pressure process. It is an isobaric process. So for isobaric process, Q is equal to delta U plus W. So delta U that is equal to Q minus W. So delta U2, Q is 100 joule minus P delta V. Right? So what is the constant pressure? 6 into 10 to the power 4. What is the change in volume? Volume is changing from 2 to the 10 to the power minus 3 to final volume as 4 into 10 to the power minus 3. So here delta U2 that is equal to 100 minus, right, what is the pressure? 6 into 10 to the power 4. What is the change in volume? 2 into 10 to the power minus 3. So here the change in internal energy into the second process is minus 20 joule. What is the resultant change in internal energy of the system? U1 plus U2. So that is equal to 400 minus 20. The change in resultant change into the energy of the system, that is equivalent to 380 joule. Right? 380 joule. Now what we need to calculate? We need to calculate the resultant heat of the AC. That is equal to change in internal energy plus work done by AC. Right? So QC that is equal to change in internal energy 380 plus work done by AC. Now what is work done under the AC process? Right? That is area. Right? Okay. This area can be divided into 2, half base into altitude and that rectangle. Okay. So we can resolve it as 380 plus area of the rectangle plus area of the triangle. So what will be the Q of AC? That is 380 plus what is an area of rectangle? 2 into, okay, so it's 2 into 10 to the power minus 3 plus 2 into 2 into 10 to the power 4. This is area of rectangle plus what is an area of triangle? That is half base into altitude. That is half, right, base it is 2 into 10 to the power minus 3 into altitude. Altitude is 4 into 10 to the power 4. 4 into 10 to the power 4. Resolving this, we are getting the value of the Kc as 460 joule, I'm sorry, right? This will be the final answer. Okay, 460 joule, A is the perfect answer. A monatomic gas at the pressure expands isothermally. Initial pressure P, V, expands isothermally to volume 2V. And then adiabatically to volume 16. Okay. First, isothermal process is going on, then adiabatic process. So at the end of the isothermal process, what is the pressure? P1 V1 is equal to P2 V2. See, first isothermal process is going on and then adiabatic process, right? So isothermal process, P1 is P, volume is V. Final we need to calculate, and this is 2V. So final pressure, that is equal to P by 2. Now adiabatic process is going on. So for adiabatic process, can I say P1 V1 raised to gamma is equal to P2 V2 raised to gamma? P1 V1 dash, P2 V2 dash. Here P1 dash will be equivalent to P2. So it's P by 2, right? 2V whole to the power gamma, right? P2 dash we need to calculate, and final, that is 16V whole to the power gamma, right? So resolving this, we are getting P2 dash is equal to, right, P by 64. Okay, we are taking gamma value as 7 by 5. You can take gamma value as 7 by 5 or 1 by 4, right? But mathematically you can resolve it to get the answer as P by 64. 2014. Now this is one homework from my side that is asked in NEET 2018 paper, right? You can answer this question right beneath the video, right? You can answer this question beneath the video. Okay. Now, till now we have moved on to the fundamentals, equilibrium, zeroth law, first law, all of those definitions. Now it's time to move on to the remaining part of the chapter, that is second law of thermodynamics, heat engine, heat pump, the relevant efficiency equation, and the Carnot cycle. It's a very easy thing, you all are aware of, right? We have to just see the formulas and sums to it, right? So let's move on to the second law of thermodynamics. So students, let's move on right to the second law of thermodynamics and the remaining part of this session, right? It is quite simple, right? We should not have to worry about that, right? It is really quite simple. Okay, so now second law of thermodynamics, basically it is having two statements. The first statement, that is given by Kelvin Planck, and second, that is a Clausius statement, right? Kelvin gave this statement of the second law of thermodynamics, right, for the heat engines. Clausius gave the second law of thermodynamics statement for heat pumps and refrigerators, right? This is only the difference. And with that, if at any situation, if the Kelvin statement is getting violated, right, it means that Planck's statement is also getting violated, right? If the Kelvin statement is getting violated, it means that, right, yes, Planck's statement is also getting violated. Now, before moving on to the second law of thermodynamics, let's understand what actual, right, is the working of the heat engine, what actual is the working of the heat pump, how refrigerators are working, and how we are able to calculate them, right? I'm extremely sorry, how we are able to calculate the efficiencies of those cycle. Again, we'll come back to this and we'll discuss this two statement, but first of all, let's move on to the heat pump and heat refrigerator. What is a right working of a heat engine? Very simple. There is one source, there is one sink. Naturally, source is at the higher temperature, sink is at the lower temperature, then we are completely, right, sure about it that heat always flow from the higher temperature to the lower temperature. Heat always flow from higher temperature to the lower temperature. Now in this case, what will happen, right? In this case, what will happen? whenever the heat flows from the higher temperature to the lower temperature, right, we are getting some specific work done. That is heat engine. Reverse phenomena, heat pump or refrigerator. There is a slight difference between heat pump and refrigerator, but generally from a theoretical point of view, we are considering both, right, both as the same. Why? Because both are having the same motive, right, to pump out the heat from the specific area. You can see this visualization, right? There is one piston attached, right, and it is performing the rotatory motion. Okay, so whenever okay, apart from this, let's move on to the, rather than this, let's move on to the simple diametric explanation of it. Heat engine. If I'm talking about the heat engine, let us check in two different. This is source. It is at the temperature T1, right? And here we are having sink. Sink is at the temperature T2, right? Source is always greater than, right, the temperature of this sink. Source will be always at the higher temperature, right? And sink will be at the lower temperature. Now here, right, heat, whenever there is a temperature difference, whenever there exists a temperature difference, either between system or surrounding, or between the two objects or two parties, right, whenever, right, okay, then heat will flow from the higher temperature to the lower one. So here, there exists a temperature difference between the source and sink, yes. So it means heat will start flowing from higher temperature, right, to the lower one. At that point of time, right, when this heat engine was about to get invented, we thought, let's take advantage of this natural flow. Let's take an advantage of this natural flow. Suppose if two bodies are brought in contact with respect to each other, one is at the higher temperature, second is at the lower temperature, obviously heat is going to flow from higher to lower one. Let's take an advantage of this natural process. Are we not taking the advantage of any hybrid, hydroelectricity, whatever, are we not taking any advantage of whatever the water is flowing? We are not able to, we are generating the electricity from that, na? We are naming it as a hydropower. Like from water we are generating the electricity. Now this is one of the natural resources, right? The same thought we had while we were dealing with the heat engine. If this is at the higher, this is at the lower one, then why should we not take an advantage of it, right? Okay, why can't we have a useful work from it? So whenever the heat flows from the higher temperature to the lower temperature, obviously, right, we are having some useful work done. Step one, right? When heat flows from higher temperature to lower temperature, useful work is output. Useful work we get. Suppose let us take an example, the Q amount of the right heat that is right moving on from the source, W amount of the work is done, Q is getting immersed into the sink. So can I write down this statement? This work done, it is as because of the difference between 1 and 2. This work done, that is as because of difference between 1 and 2. Now, this is an actual process of the heat engine. It's very simple. There might be some efficiency. See, whenever we are dealing with any kind of the cycles or any machinery things, right, we always used to consider the efficiency. And it is for sure, it is a very simple thing also. Whenever you are giving input to something, to someone, you are expecting an output. And as of human nature, we always expect 100% as an output, right? So yeah, if it is giving something, right, we are getting something as an output. What is an efficiency? Efficiency, can we say output whole divided by input, right? In the heat engine, are we not getting the output as a work done? We are getting output as work done or not? Yes, we are getting the output as a work done. So efficiency, that is equal to output by input. Output is a work done. This is heat supply. This is an actual formula of the efficiency. What is the work done? Can I say it is Q1 minus Q2 whole divided by Q1, right? So this is the formula of the efficiency of the cycle. Another formula of the efficiency in terms of the temperature is this, right? This is, okay, T2 you all are aware of. T2 is the temperature of sink and T1 is the temperature of the source. T2 is the temperature of sink and T1 is the temperature of the source, right? So this is the formula of the efficiency of the heat engine. As you all are aware of, efficiency is never 100%. As you all are aware of, efficiency is never the 100%, right? So this is what all about the heat engine is. We are getting input as Q1. See, this is a natural thing is going on, right? Naturally, it doesn't mean the heat engine is a kind of the natural resources. No, right? From source and sink sinks are connected. Heat is flowing from source to sink. We are getting a specific output. That much simple is it is. But if we are talking about the heat pumps, then this is the reverse phenomena, right? Okay, this is the reverse phenomena of heat engine. Reverse phenomena of the heat engine. Why? This is a reverse phenomena. See, you can see in this visualization. Condenser, to make things cool, it releases the heat. Slowly it is coming back, right? In the previous case, we were getting output as a work done. Here, what is the main purpose of this condenser? What is this main purpose of this condenser? The main purpose of the condenser is to pump out the heat so that the area from which heat is pumped out remains cold. Right? This is in another, this is not actually, right? This is one of the examples, right? Condenser is pumping out the heat, right? And we need to add some useful work, right, to maintain the temperature. Now let's see this, right? See, again I'm taking, this time I'm taking sink, this side with the temperature T2, and I'm taking source at this side. Now, what is the main purpose of the heat pump? What is the main purpose of the heat pump? To pump out the heat so that temperature of sink remains cold. What is the natural thing? From higher temperature to the lower temperature, heat flows. But reverse phenomena of that, right? Reverse phenomena of that. We need to maintain the temperature of this sink. But as of the sources at the higher temperature, continuously we are getting some input. And if we want to maintain the temperature of the sink, then what we will do? We will continuously pump out that receiving heat. Continuously the heat, right, will be pumped out and the temperature of the sink will get maintained. Best example of this is a refrigerator. The inside temperature of the refrigerator is maintained at -9. And whenever, if you have, see, a refrigerator is that kind of the device is present in everyone's home. It is a kind of the electronic appliance, right? It is a mandatory and it is needful also, right? So whenever you will if you have enough time, just move on to the kitchen wherever it is kept, right? Okay, just open the door of the refrigerator. You will maintain a cold. You will feel a cool environment. But when you will move on to the back side of the refrigerator, right, one thing you will analyze, right? You will hear a voice of like that. That voice itself states that, right, the machine inside is continuously pumping out the heat in the surrounding. The back part is warm. The back part of the refrigerator is warm. Why? Because machine inside it is continuously trying to pump out the heat from the refrigerator to the outside environment, so that the temperature of the refrigerator should be maintained, and things inside it should have a cooled environment. So it means that suppose if you want to apply the reverse phenomena, you need to give the work. Suppose this with the help of the condenser, right? Okay, this is pumping out the heat Q1, right? For this working, we need to give some work. How condenser is getting operated? We need to give some work now. So in the previous case, we were getting work as an output. Here we are giving the work as an input, right? Yeah. Work is input, right? So that condenser can, right? Work is input so that condenser can blow out the heat, right? It can pump out the heat. So here we are having coefficient of performance. Here we are not having the right efficiency, we are having the coefficient of performance, that is Q, that is pumped out, whole divided by input. Q, that is pumped out, whole divided by input, right? And suppose the resultant of this two, it is getting added into the source. So here can we write down it as Q2, that is equal to Q1 plus W, right? So this coefficient of performance, this is a symbolic notation of coefficient of performance, that is Q, right, that is pumped out, or in another sense coefficient of performance, that is equal to, right, Q that is pumped out is Q1 whole divided by W is equal to Q1 minus Q2. This is the value of the coefficient of performance. And this is how the heat pump works. So on basis of heat pump and heat engine, right, Kelvin and Clausius gave two most important statements. Kelvin and Clausius gave two most important statements. Now let's move on, right? Let's move on to that two statements of the second law of thermodynamics, right? Both statements are same, right? There is just an grammatical. Okay, Kelvin said that it is impossible to construct a heat engine with 100% of efficiency. It is not possible, right, to construct an engine that is having the 100% of efficiency. It means that it is not possible that whatever the heat is flowing on from the source to sink, 100% of it is getting converted into the work done. No, it is not possible, right? It is not possible. It is not possible, right? What does a Clausius statement indirectly? It is saying always energy losses there. See, these are not an exact statement. This thing you'll find into the resources. It's not a big deal. What actually this statement tells us, right, that I am writing in front. Many thousands of times I have told you, right, that thousands of things you are going to get into the available resources, into the exact technical form. But are those things really understood by you all into the most convenient manner? No. So whatever the physics that I am representing in front of you all, right, it is like that. It is represented that way, that it should be easy to understand, right? So here that thing I've kept. There is one Kelvin statement, 100% efficiency is not possible. Second, energy loss is always there, right? Both write down, both have given the different the same statement but with the different grammatical formations. And at last, at the note, it was written, if any engine is violating the Kelvin statement, it means the Planck statement is also getting violated. So this is all out about the second law of thermodynamics. Right now, let's have some sums on it. And finally, say NEET 2018, the sum based on this was asked. The efficiency of an ideal heat engine working between the freezing point and the boiling point is. Freezing point 0 degree centigrade, 273 Kelvin. Boiling point 100 degree centigrade, 373. What is an efficiency? 1 minus temperatures of sink by temperature of source. Efficiency, that is 1 minus 273 by 373. Efficiency, that is equal to 26.8%. A is the perfect answer for that, right? The temperature inside the refrigerator is T2. NEET phase 2 2016. Before that, let's move on to another sums. The temperature inside NEET phase 2 2016. The temperature inside the refrigerator is T2. Let's draw the diagram first. This is T2, right? This is T1. This work done we are giving, this is value of Q1. The amount of the heat delivered to the room per each joule. Q1 is getting pumped out. W is work added. Q2 is released in the room. Why it is released in the room? To maintain the temperature of the sink. This is a question of heat refrigerate. What we need to calculate? The energy that is released in the room per each joule of electrical energy, means per work done. To operate this engine, obviously the external work needs to be done, and obviously it is an electrical energy only. So here, coefficient of performance, that is equal to Q1 by W, that is equal to T2 by T1 minus T2 in terms of Kelvin, right? In terms of Kelvin, right? So if you want to write this, you can write it plus 273. But what we need to calculate? We need to calculate Q2 by W, right? There is one relation. Can we write Q1, right, plus W, that is equal to Q2. So if you are writing it as Q1 by W plus 1, that is equal to Q2 by W. Here we will get the value of the Q2, right? Now what is the value of the Q1 by W, right? Okay, so this will be, right, T2 by T1 minus T2 plus 1 is equal to Q2 by W. So finally we are getting it as T1 by T1 minus T2 is equal to Q2 by W. But here 273 will be added because things are written into the Kelvin. This will be the perfect answer for this specific question. One formula, it is rotating again and again into the different part. B is the perfect. This is what all about the second law of thermodynamics. Which of the following process is reversible? Obviously it is an isothermal compression, right? Okay. Why it is reversible? Kindly answer this. Why this is reversible, right? Beneath the comments into the video, beneath that, right? I need answer of all of this, right? Okay. Let's move on to the last topic of this chapter, that is Carnot cycle. It is very easy. Formula is very easy, right? And we are not, what we can say, only 1 to 2 formulas are there, and really. Carnot cycle. To understand the Carnot cycle, right, lots of examples in thousands of books are given, right? It is an ideal cycle. Sometimes the students used to ask, sir, whether this cycle is possible or not into a day-to-day life, right? Okay, so I must say no. This is an ideal cycle, right? Ideal cycle without loss, right? It is violating the Kelvin and Planck, but it's okay. We are moving on to the theoretical aspects, right? So we don't have to worry about it. Carnot cycle. One simple process I am talking about. Have you ever ride that moped or bicycle? Not moped, the geared bike. You are having 6, some bikes are having 5 gears. 1, 2, 3, 4, 5, like that. Some are having 4 gears. 1, 2, 3, 4, like that. Some are having 4 gears but towards the back side. 1, 2, 3, 4, like that. Right. I'm not talking about the gears. I'm talking about that how engine is made. How many strokes the engine is having. To understand the Carnot cycle, right, I'm going to show you all one process, right? The process of the 4-stroke engine. Right, the process of 4-stroke engine. There is one combustion chamber, right? Piston is there, right? Here we are having outlet wall. Here, right, we are having inlet wall. Right, at one side we are having outlet wall. At one side we are having inlet wall. Yes. I'm talking about that 4-stroke engine that you are daily used to, right, in your using in day-to-day life, that vehicles. Some vehicles might contain 4-stroke engines, some might. Stroke doesn't means gear. No. Stroke means in how many stages the cycle is getting operated. Right? A simple 4-stroke engine. I am giving you all the 4-stroke, the example of the 4-stroke engine to understand the Carnot cycle. It is an analogy to understand this, because Carnot is also having the 4 stages and this engine is also having the 4 stages. That's why I am telling you all. Stage 1, right? The fuel is getting inside the combustion chamber. Now, whenever the fuel is getting inside, this chamber is thermally insulated. You all are aware of. It means whenever the fuel will get inside, the temperature of the inside environment will be constant. It is a first stage, isothermal expansion of the fluid. Now, second stage, inlet wall gets closed. Now, piston will start its working. I'm sorry. Rapidly it compresses the fluid or expands. Compression, expansion. Like this way. Let us take an example, right? Instead of a fuel, you are taking the rubber pad. Right? Rapidly this thing is going on. Right? Why this rapidly thing is going on? Because 4-stroke engine generates, right, the spark, or in another sense it generates a power on which, right, the vehicles are working. The vehicles get energy from this part. First, the fuel is getting inside the combustion chamber. While entering inside right, temperature, because these are the thermally insulated object, right, this walls, right? So everything goes on with fuel is getting expanded, right, in the isothermal expansion. Second, process is quite rapid, right? So that there is no time for heat exchange. Now, rapidly, fuel is getting compressed. Third stroke. Fuel is getting rapidly compressed so that to generate an energy, so that for, right, the working of the vehicles. Third, fuel is getting, everything is going on at the constant temperature inside, right? So it is isothermal compression, the third stage of the Carnot cycle. Compression is so much rapid, right, that the system is not having time to exchange the heat. The fourth stage, adiabatic compression. This was just an example, and finally, right, when the pistons moves up, the appropriate power is generated, right, the dirt goes out through the smoke, the outlet is removed from the smoke. Okay, so this is one of the example, right, the waste is removed like this way. This is one of the simple examples, right, very simple example, and the four-stroke engine is an analogy, right, given by, okay, proposed by me, so to understand the four stages of the Carnot cycle. So now we are completely aware of, we are having the four stages of the Carnot cycle. First stage, that is isothermal expansion. Isothermal expansion, right? It means that here the temperature is P1 V1, second part it is P2 V2, and that is equal to constant. In this case, work done, it is defined as 2.303 nRT log of V2 by V1. The first stage of the Carnot. What is the second stage of the Carnot engine? Adiabatic expansion. In this stage, the net heat flow is 0. So here the work done will be in between, see, this is second to third, right? This is first to second. So here work done is equal to P2 V2 minus P3 V3, right, whole divided by adiabatic index minus 1. The third stage, isothermal expansion, adiabatic expansion. Now compression will move on, right? Because as given you the example, compressing, like this way the phenomena is going on. The four-stroke engine is only an analogy and presented example. Please don't hit it into the mind, right? Because there are some limitations in that. We can't exactly compare four-stroke engine to, right, the Carnot, but there are some limitations of it. But through an analogy, it is good. Third is isothermal compression. Here we are having the equation as P2 V2 raised to gamma, P3 V3 raised to gamma. Isothermal compression. For isothermal compression, right, isothermal compression states that, right, it is P3 V3, this is going on from 3 to 4, P3 V3, that is P4 V4, and that is equal to constant, and work done in this case it is a compression, right? So work done, it is negative of 2.303 nRT log of, right, V4 by V3. The fourth stage of the Carnot is adiabatic compression. Right? Adiabatic compression. 4 to 1. Okay, the process is getting completed. Work done is equal to P1 V1. I'm sorry. Right, P4 V4 minus P1 V1 whole divided by gamma minus 1. P4 V4 to the power gamma is equal to P1 V1 whole to the power gamma is equal to constant. From all of this, right, the efficiency of the Carnot engine is given like this way. That's okay. Right, this is the efficiency of the Carnot engine, and this is what the entire cycle is all about, the four stages. Right, this is only the why I kept the four-stroke engine, right, because four-stroke engine is only the way, right, the best way, right, as an analogy to understand this concept. Right, Carnot engine having the efficiency 1/10 as of the heat engine is used as a refrigerator. This question is asked in 3 times, NEET two times, NEET 2017 cancelled. It might be possible that it is cancelled, that's why it's asked in 2017. A Carnot engine having the efficiency of 1/10 as heat engine Efficiency of the Carnot engine is 1 by 10. It is used as a heat engine. Suppose it is used as a refrigerator. If the work done on the system is 10 joule, work done on the system is 10 of joule. The amount of the energy absorbed from the reservoir, right? Amount of the energy absorbed from the reservoir at the lower temperature is what? Amount of the energy that is absorbed from the reservoir. Okay, it is what? Right? Amount of the energy that is, right? Amount of the energy, right? That is absorbed. So first of all, the efficiency, right? Efficiency is, right? Efficiency is what? 1 by 10. So first of all, if it has been used, the efficiency is as a heat engine. So can I say efficiency, that is work done whole divided by Q, right? Work done, that is whole divided by, here work done is 10 joule. So Q, right? That is work done by efficiency. Efficiency is 1 by 10. And here it is 10 joule. So 10, 1 by 10, right? So Q, that is equal to 100 joule. This much amount of the heat, right? What does this say? This is output by input, right? Input is 100 joule, right? When the Carnot engine, see, efficiency of the Carnot engine was 1 by 10 when it was using as a Carnot engine having an efficiency of 1 by 10th of the heat engine, right? If heat engine is giving 60, then Carnot engine gives 1 by 10th, right? In that, work done is 0. Now suppose if Carnot engine is used as a refrigerator, suppose this is a refrigerator, this is a sink T2, right? This is a source T1. Here we are getting the value of the Q1, here we are giving the work done, and here we are getting the Q2. So this Q value that we are getting from this efficiency is the amount of the heat that is released in environment. Q1 plus W, that is equal to Q2. Q1 is equal to Q2 minus W. What we need to calculate? The amount of the energy that is absorbed from reservoir, and that is at the lower temperature. It means how much energy that is pumped out, that we need to calculate. It means Q1 we need to calculate. So that is 100 minus 10. 90 joule is the perfect answer. One and the same formula, just used into the different way. That's it. Now let's move on to the next sum, right? The efficiency of the Carnot engine is 50% and the temperature of the sink is 500 Kelvin, right? So first of all, efficiency, it is C. Efficiency is 50%, right? And temperature of the sink, we are having it as the 500 Kelvin. If the temperature of the source is kept constant and efficiency is raised to 60%, if efficiency is raised to 60%, right, then required temperature of the sink will be what? First of all, let's calculate the temperature of the source, right? It's sink by source, right? It's 50%, and that is 1 minus what is the sink? 500 Kelvin whole divided by source. It's 50 by 100. So here the temperature of the source we will get as 1000 Kelvin. Now this thing is kept constant and the efficiency is increased to 60%. Again 1 minus T2 dash by 1000 Kelvin, right? Now this is increased to 60%. So 1 minus T2 dash by 1000 Kelvin. Resolving this, you are getting T2 dash as the 400 Kelvin. This is the new temperature of the sink. If efficiency was 50%, right, sink was at the 500 Kelvin, right, then the source is 1000. Now suppose if we want to increase the efficiency, but they have mentioned into the question, but we have to keep the source as a constant. So we keep the source as a constant, efficiency is increased, right, and finally again applying the same equation, we are getting the temperature of the sink 400 Kelvin, right? So this was a sum based on the Carnot. This is a question from my side, homework. This is a very nice question. You can answer this right beneath the video, right? Okay. What happened, bro? Okay. This is also another question homework from my side. Okay. So guys, thermodynamics. Let's see, right, what we have seen, right, from the beginning. Just have a glimpse of it. Okay, so that it is easy to understand. Thermodynamics, we moved on to the flow chart, right? We moved on to the Zeroth Law of Thermodynamics, equilibrium, types of equilibrium, right? Thermodynamic processes, all the processes and the respective work done, right? Okay, after that, polytropic process, its graph, internal energy, first law of thermodynamics, all of the shortcuts, right? Graph shortcuts and everything we saw. Okay, it's okay. Right. Everything, right? Finally to the Carnot engine, right? And some of the sums, right? Homework. Carnot engine, heat pump, heat refrigerator, second law of thermodynamics, all of the sums, right? So okay guys, it's time to go now. In the entire part, right, only two chapters are remaining, SHM and waves, right? So students, it's time to go again. We will move back, right? We'll come back, right, in the new part in SHM and waves. Okay, and yeah, most important thing, I will be waiting for all of your comments regarding this video and the teaser right beneath, right? Kindly comment, please, right? So guys, it's time to go. This is Indrajeet Singh signing off from the desk. Bye bye, Sat Sri Akal, and namaste from my side. Bye everyone. Stay at home, stay safe, stay healthy amidst the pandemic. Bye.